Mimosa pudica is low, much-branched, generally perennial, slightly woody at the base, from 15 to 100 centimeters high, and has either an upright or a low trailing habit. Its stiff reddish-brown or purple stems bear scattered thorns. The hairy leaves are alternate and compound. The pink flowers form small globular heads, each borne on a short hairy stalk rising from a leaf axil. Mimosa pudica is remarkable because of its sesmonastic movements, which are touching the leaves, shaking the plant, slight warming of the leaves, chemical and electrical stimuli, or subjecting the plant to a lack of water, will cause the leaflets to fold together and the whole leaf to drop downwards temporarily. Pulvis is a region with special cells, called motor cells, situated at the base of leaf petioles. As the volumes of the cells on opposing sides of the leaf or leaflet change, so one side swells as the other side shrinks, thus causing the leaf to move. The left picture shows that changes in the pulvinous shape could affect the direction of the entire petiole and individual leaves. The middle cartoon indicates that filling the central vacuole with water can change the shape of the cell, pushing in one or more directions. The right image shows just how the extensor cells on the bottom must be inflated to lift the petiole, while turgidity in the flexor cells makes the leaf drop.
Mimosa pudica has compound leaves. Compound leaves are beneficial because it takes in better ventilation for deep parts of the plant, which is caused by leaves folding when touched. It also reduces water loss by transpiration, which is caused by leaves folding when heated. It helps absorb daily light, which is caused by leaves folding in absence of sunlight.
Mimosa pudica helps in nitrogen fixation. Nitrogen fixation is a process by which nitrogen N2 in the atmosphere is converted into ammonium NH4. Atmospheric nitrogen or molecular nitrogen is relatively inert. It does not easily react with other chemicals to form new compounds. The fixation process feeds up the nitrogen atoms from their diatomic form to be used another way, which helps in farming. It was discovered that the weed has solar properties suitable for the production of solar cell electricity. It was possible to construct a functional mimosa solar panel with the plant extract. The solar panel is designed in such a way that the electrical potential of the cells can be restored on exposure to direct sun rays after they have been discharged.
The case study is two-story office building, having a GFA of 780 am square meters. The building consists of a cubical massive body acting as a uniform base for a dominant eye-shaped mass at the top front edge of the building. Choosing this building to apply the improvement strategies was challenging because it's already designed for natural ventilation and daylighting. The building is located in Sas al-Nakhl, one of Abu Dhabi's suburbans. Abu Dhabi's prevailing winds all the year are from the east, south and northwest directions. The wind temperature is pleasant in the winter season. This chart summarizes the Mimosa pudica's behavior and how can it be applied to the building. The leaves' interaction with touching can be applied to the building through providing means of interaction with the wind. The list on the right side shows a summary of the design methods which will be used to achieve the environmental strategies on the left. Wind turbines will be used to harvest the free energy of the wind. Smart screen and relocating the existing skylights of the building will be used to reduce the heat gain. New skylights and light tubes will be added in order to achieve better daylighting inside the building. New openings and apertures will be installed in order to improve the natural ventilation. PV panels will be used in order to harvest the free energy of the sun. The smart screen is an external screen which will cover the building's longitudinal facades as well as some portions of the roof where regular occupied spaces are underneath. This screen is designed to change its configuration according to the climatic conditions. It will interact with three major climatic factors: heat, wind, and light. The screen has three main positions or modes. The first one is the double screen mode, and it is designed to completely cover the facade. It's also designed in a twister manner to create pressure differences that promotes air movement and avoid hot air trapping. The second mode is the windbreak mode, and it will take place in the presence of direct and diffuse solar radiations and wind streams. It will reconfigure to form wing walls which will capture the surrounding wind streams and redirect it toward the building. The smart screen is oriented toward the prevailing wind direction, which is the northwest, with windbreaks integrated to harvest the maximum amount of wind. The third mode is the shading louvers mode. It will take place in the presence of direct solar radiations and absence of diffuse solar radiations. This screen will reconfigure to form horizontal and vertical louvers. The louvers were designed carefully in order to avoid trapping hot air or reflecting the heat onto the building. The fabric material of the screen has been chosen carefully to balance between the solar transmission and the transmission of the visible light in order to achieve the target protection while do not block the natural sunlight. The screen will be automatically controlled by software loaded with the annual predicted climatic conditions. However, this can be overridden by the data received from the weather station on the roof of the building, occupant control in each space, light sensors, and occupancy sensors in each space. Running the calculation on the Ecotech analysis software, it was found that the screen has a negligible impact in reducing the energy consumption of the building. This is probably due to the small glazing areas and high efficient glazing already being used in the building. The second design strategy is relocating the existing skylights in the building and adding new light tubes. This strategy consists mainly of two major changes. The first is excluding the huge atrium in the center of the building from the air-conditioned space. This is because it was increasing the building cooling load tremendously, while it was only providing the lighting for a rarely occupied space. The second change is adding new skylights in the regularly occupied spaces on the first floor and light tubes in the regular occupied spaces on the ground floor. After running the calculations on the Ecotech software, it was found that the first change, which was excluding the atrium from the air-conditioned space of the building, has achieved 22% reduction in the energy consumption of the building. It was also found that the second change, which was adding new skylights and light tubes, has improved the daylight levels in the deep spaces of the offices on the ground and first floor, which were not achieving the minimum acceptable level of daylight previously. The fourth design method is installing wind turbines for electricity generation. A mini wind turbine will be located at each side facade in addition to two turbines on the roof level. The turbines will be located carefully down the wind at points where the highest air movement is expected. A small low wind turbine by Honeywell was chosen to be installed. The turbines on the roof are expected to operate continuously, while those on the side elevations will operate only in the double scheme mode of the smart screen. The expected power output of a single turbine is 1580 kilowatt hour per year as per the technical data received from the manufacturer. Installing 4 turbines will result into 3% reduction in the energy consumption of the building. Fourth design strategy, installing solar collectors. 3 locations were studied for the PV panels installation. First, the fabric of the smart screen. Second, the top roof of the building. Third, the cover of the car parking adjacent to the building. The first and the second options were excluded because they were found to increase the thermal mass of the building. Accordingly, the third one, which is the cover of the car parking, was the one chosen for installation of the PV panels. Using the solar window analysis, the best orientation for the panels was found to be towards the south at a tilting angle of 30 degrees. The expected power output of the PV panels is 300 megawatt per annum. The building energy consumption is 280 megawatt per annum, which means that the PV panel output is expected to reduce 100% of the energy consumption. The last design strategy is the ventilation openings. The aim of this strategy is to improve the air movement inside the building spaces. This will be achieved through cross ventilation and stag ventilation. The new provided air outlets will be larger than the air inlets and higher in level in order to create a maximum pressure differences so that the greatest amount of air is drawn out of the room space. This strategy will work in collaboration with the smart screen windbreak mode, which redirect wind towards the building.